We are now able to create a basic map by simply jotting down all the points that the robot records onto a plot and look at the result. As you can see, this turns very slow pretty quickly because we do not differentiate between individual points but keep every reading that the laser scanner ever has made. And as you know, this can become megabytes in a few seconds, if not more. So one other way to do this is to use a grid map, and for this we have implemented a display. In order to show the display in case it's gone, you have to click on the robot and then go to display devices and say show display overlay, and I've implemented some basic mapping here. As the robot goes around, I'm jotting down the points on a grid. This is a 300 by 300 grid. That means once this point, one of these points is set to be white, it stays white and the memory kind of stays constant, although it's still not a very efficient way to store a map. But this is something we will address in later courses in this specialization. Now, as the robot goes around, you see how the grid is filled up, and I've also drawn the actual position of the robot in red. Now you might wonder why it's white. This is because we have agreed on setting infinity values that the laser scanner produces to be to 0, which essentially lets the robot detect a point wherever it is when that happens. So in order to avoid this, I recommend to use a different way of dealing with these errors. And in this case, we want to not set those to 0, but we want to set them to some kind of large value like 100 meters, which we know will never show on the map. Now if you do that, then you can see the white marks on the robot's trajectory go away, and we see a red trajectory where the robot is driving. You might also wonder why the odometry is so good. It is not. I have implemented a GPS and a compass. I will show you how to do this in a next video, so you can ignore the bad odometry for now and really focus on mapping. Now, the next question is, what do you need a map for? Well, one thing would be to think about the loop closure moment we had before, where we said that once the robot identifies the start line, we might say we know now at which position it is. In practice, you can use any of these objects as a beacon and localize yourself kind of like a light tower in navigation of ships. This is something we will teach in a later course in this specialization. But what we will do now is to use a map like this for navigation. Now you might ask, how can the robot possibly know whether space is navigable or not? In order to see where the robot can travel, I would need to compare every point on this map with every point on the robot's body. There's an easier way to do this, which we will teach you here, which is called the so-called configuration space. And let's speed this up a little bit. What you can do is you can actually grow the obstacles by a certain amount, which will make the remaining space 100% navigable for the robot. And this is best understood with an example. Now the robot created this map here, and now we do see a version of the configuration space, which is essentially this map that the robot has been constructed, and every pixel in it is grown by what is called a kernel of size 20 in this case. Now, how is this useful? You have to threshold this and say, okay, if the chance that a pixel is occupied is more than 90%, I consider it an obstacle, and you will get something like this, which is now a threshold version of this map that you've just seen. And now you can, given that the kernel has the right size and completely encompasses the robot's width, you can assume that everything that is blue here is fully navigable for the robot, and abstract the robot to be a single point on this grid map. Finally, there are different ways of dealing with noise. Instead of simply writing down every point on the map as the laser sees them, we can also say that whenever a point gets registered, we add the chance to be an obstacle there to be 1% more. And now you see the obstacles are emerging out of the dark, and the more often the laser hits on them, the more likely it becomes that we have an obstacle there. So this is very powerful in conjunction again with thresholding, where you can very easily remove noise. And for example, what you will see in the future, sometimes the laser hits the ground as the robot is pivoting back and forth, and you might have other recordings that you would want to remove. And this is very easily done by simply ignoring the majority of the data in the first place and only mapping them when they become very pertinent.